All right, guys, welcome to Precalculus 3.2.1. We're going to be talking about summation notation today. So to start off, we're going to we would normally do in class a little kind of experiment slash race here, where we try and see, well, how fast can we actually add up these series of numbers. So we would give you this pattern here. We're going to have, there it is, 0.01 times n plus 1.7. So we'd plug in 2 and solve it out, take that result, then plug in 3, solve it out, add that result, and then keep doing that again and again and again until we get to 20. So from 2 to 20, plug in all of those, and then adding up the results of all of those together. That would be what we're trying to do. So doing that by hand, and then I would go and stop you and see how far we all got, right? So that leads us into the idea of what a summation is, right? A summation is we're taking a pattern and we're plugging in 0, 1, 2, 3, 4, 5, 6, whatever it is, from what number to what number here. So, for instance, on this one, we're going to write out in expanded form kind of what this would be and then what this would be here. So, if I go over to my document camera, right? Our first one, we're doing, or for both these, we're doing 0.05 times 0.5, not 0.05, times 0.5 n plus 2 squared. And we want this one from 0, 1, 2, and 3. So if we do that, we plug in 0. We get 0.5 times 0 plus 2. 2 squared is 4. 4 times a half is 2. So there's my first value, right? And then if I plug in a 1, well, that's 0.5 plus 2 is 2.5. If I do 2.5 squared, and then times 0.5, I get 3.125. Now what if I plug in 2? If I plug in 2, that's 2 times a half is 1. 1 plus 2 is 3. 3 squared is 9. 9 times a half is 4.5. And then if I plug in a 3, half of 3 is 1.5. 1.5 plus 2 is 3.5. If I do 3.5 squared times a half, I get 6.125. Right? So then if I add all of those up, if I do 2 plus 3.125 plus 4.5 plus 6.125, I get a total of 15.75. Not too bad, right? It's not hard, but it is a bit tedious. Okay, so now let's do the exact same thing, but we're going to do it for the numbers 1, 2, 3, and 4. Now you can probably already kind of get, well, I know what most of those are, right? If I plug in 1, I'm going to get the same thing as I got here, 2 and 3. So it's really going to be 3.125 plus 4.5 plus 6.125. So the only thing that I really need to do is the 4. So if I plug in 4, half of 4 is 2. 2 plus 2 is 4. 4 squared is 16. Half of 16 is 8. Like 8 there. So if I add up all of those, I get, so you can see it, 3.125 plus 4.5 plus 6.125 plus 8, we get 21.75. Great, right? So those are summations, right? We just took the values, we plugged them into our formula here, and then we added them all up and got our sum, hence the term summation. Okay, so if we look here, the big thing that we're trying to figure out is what was common, right? what differences and similarities did we have? Well, these similarities were those three numbers, right? 1, 2, and 3 were used in both of those patterns. They also both use the exact same pattern of 0.5 times 0.5n plus 2 squared. What the differences one was that the first one had that 0, which we plugged in, and the last one had the 4, which we plugged in. But other than that, they were very, very similar. That's a big key thing that we want to keep in mind going forward here. So let's introduce you to the idea of summation notation. So it looks like this, right? It's the Greek letter sigma, at least the capital version of the Greek letter sigma. And it looks like this big kind of weird pointy E thing. Okay. And you'll typically see it in math context like this, right? Where the sigma means the sum of. This n is equal to on the bottom is where we want to start. So it's the first number we plug in. And then the number on top of it is the last number we plug in. So we plug in between 1 and 3. So we'd plug in 1, plug in 2, plug in 3, then add them all up. And then on the right-hand side of this, you're going to see the pattern. So this one here, it's n to the second power. So I would first plug in 1 and get 1 squared, and then plug in 2 and get 2 squared, then plug in 3 and get 3 squared. Once I get to 3, I want to stop. So I just add all of those up and I get 14. So then 14 is the summation of 1 to 3 on that pattern of n to the second power. Okay, so that's kind of what these mean. The n squared part, that's called the argument of it. The n part, where it's like between 1 and 3, that's the index. Don't worry too much about those particular terms. The argument you'll probably talk about a bit more, but in general, that's just kind of what sigma notation is for. And it lets us do these summations a whole lot faster and a lot more efficiently than trying to like write out, hey, do this for this number, this number, this number, this number, this number, this number, and so forth. Right? Okay, so let's try that out. Okay, so here are a few problems in sigma notation or summation notation. So go ahead and try and solve those out, right? So this first one, they've already expanded it for us. So first we want to expand it. So this would be 2 raised to the third plus 2 raised to the fourth plus 2 raised to the fifth plus 2 raised to the sixth because it's from 3 to 6 under the pattern 2 raised to the j. They're going to change around the number. Typically it's n or it's k. They use j and m just to show that, hey, it can be whatever, but as long as you're consistent, not a huge deal, right? So then figure out what the total is there. Then do it here, where they've only partially started the expanded form, and then on C and D fully expand it, and then add all of those up. Okay. All right. So go ahead, pause, try that out, and then come back here. All right. So hopefully you've done that. What I'm going to do now is show you how we can check those on a calculator. Right. I'm going to show you on the TI-84s. If you are at home and you don't have access to one, if you just Google summation calculator, you should be able to find one pretty easy. There's quite a few ones that are decent. So just find one that you kind of like and use that for when you're at home and you don't have access to my calculators at school. So if I pull over this, so our first one there, to get to our summation notation, we're going to go to the math button, which is over here underneath alpha, right? And then it's under the math menu, but it's really far down. So if you just hit like up once, you'll jump down to the bottom and you can go up to summation, which is option 0 there. Hit enter. Nice thing about these ones is it tells you, it gives it to you where it looks like it should. Older versions of TI-84s or 83s, they're going to have it's going to say like sum and then parentheses, and you have to put in these values with then commas in between them. Look it up online what the code is to do that, because you have to put it in the right order with commas. But for ours, you can just kind of follow along here. So we want to look just like it looks there. So you can use whatever variable you want. I'm always going to use X on a calculator because it's just way easier because there's just one button for it right there. There's my X. So I want to go from 3 until 6. And the pattern is 2 raised to the j power, or in my case, 2 raised to the x power. So then I hit enter, solves it out, and I get 120, right? So this kind of takes out all that tedious bit, which is kind of we'll plug it in, enter, plug it in, hit enter, plug it in, enter, then add them all up, right? Now that I'm showing you this, I'm never going to force you to do it by hand anymore. Okay. Our second one, we're going to do, again, math, summation. We want x from 3 till 5, and we're going to be following the pattern of 4 times x squared plus 2. And we should get 206 for that second one. Right? Then, once again, I do the summation of x from 1 to 5, and I want to follow the pattern of 16 times 1 over 2 to the x power. You should get 15.5 on that one. And then finally on D, do summation of x from 1 to 4. Our pattern here is 1 over x times x plus 1. And we get 0.8 on that one. Okay. So again, hopefully you got those answers, and that is how we can do that on a calculator. And again, when you're at home, if you just want to Google a summation notation calculator, you should be able to find some of those. All right, let's move on to the next bit here. So 88 through 91, I want you guys to go ahead and work through this as best as you can. I'm just going to 88 is just kind of going to approach that in the same way, but we're going to introduce a problem which can happen here. So go ahead and work through those, see what you can do, and then come back here and I will walk us through it. All right, so on 88, we should notice that the problem is they're not counting by whole numbers, right? We didn't explicitly mention it in the past year, and you've already kind of done these things, but we count by whole numbers, and the sigma notation stuff, it does it by whole numbers, because otherwise there's an infinite number of numbers between 5 and 7, and you could add up every single one of that infinite number of things and get a very different answer than if you just add up the nice whole integer numbers there, and that's what the notation will typically do. So that's the problem with number 88. Now in 89, they're saying, well, we actually want to try and break up this region between 2 and 3 into 5 even pieces. So I hop down here and I look at this. So we're looking at regions of numbers between 2 and 3. So here's 2, here's 3. I want to break it up into 5 even regions, right? So the distance here is 1. So if I just do 1 divided by 5, I get 0.2, right? So then my regions are going to be a distance of 0.2. So here is 2.2, 2.4, 2.6, I'll do it in here, 2, 2.2, 2.4, 2.6, 2.8, and 3, right? If I break up my number line like that, I end up getting 5 even regions. I did that by saying, well, my distance between here and here is 1. So that distance of 1 divided by wanting 5 regions, each region needs to be 0.2 long. So I got that. Okay, so there's the diagram of those intervals. So list the left end points of each subsegment in a sequence. Then write an equation for this sequence. Okay, so this is the kind of weird part. So I want this number, this number, this number, this number, and this number. Okay, so I want an equation that kind of gives me those, right? So this is my first, my second, my third, my fourth, and my fifth number. Okay. So I'm actually going to rename these zeros. Sorry, 0, 1, just so that we kind of stay consistent. 2, 3, and 4. 0 because it's my initial part that I'm actually going to start with, and you'll see why that makes this a little bit easier in the future, right? So I want to figure out how can I have stuff count by this, right? Count by 0.2s as opposed to counting by whole numbers, right? So I need to start at 2. That's my initial starting point, but then I'm also I'm increasing by 0.2 each time. Well, that's like a rate of change, right? I'm increasing by 0.2 each change. That's basically a slope. So I can say plus 0.2, I'll call it n, as opposed to x. But really, here's a slope, here's my x, here's my y-intercept, or my initial point, which is why the 0 helps. So now, if I plug in n is 0, I get 2. If I plug in n is 1, I get 0.2 plus 2, 2.2. If I plug in 2, I get 0.2 times 2 is 0.4, 2 plus 0.4, 2.4, and so forth, right? So now this, we'll model this from n being 0 to n being 4. Okay, awesome. Well, what if I want to do this from right end points, which is us saying, well, I want here, 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 and here, right? Because those are the right numbers of each of these 5 segments. We just did the left side, left, 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 left. Now let's do right. Right, 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 right. So to get those ones, well, I could call this 0 now, but if I use this exact same notation, really I'm doing the same pattern of 2 plus 0.2n, but I'm going to do it from n being 1 till n is 5. So this is effectively the same thing as we kind of saw earlier, right? One of the very first problems we did today was, well, if I just use the exact same pattern and change where I start and stop, I can either use this and the middle bits, or this part and the middle bits. Okay, so that seems kind of weird and off track, but we're getting to a place where we're going to be using this, and it's going to be very, very helpful for us. So over here on problem 90, right? So a series is the sum of terms in a sequence. Use the following series written in expanded form to complete the parts below. Use sigma notation to express the sum. Okay, so how can we do this, right? I got 0.36 plus 4 plus 4.4 plus 4.8 plus 5.2. Okay, so it's going to be very similar to what we just did, right? So let's hop over here and know that I want 3.6 plus 4 plus 4.4, I'll put 4.0 just to be consistent here, plus 4.8 plus 5.2. So I'm going to call this my 0th term, my first, second, third, and fourth term. Okay, so if I want to add all of those up, I need what pattern those are following. Well, I'm starting at 3.6, and I'm increasing by how much each time? Well, I'm increasing by 0.4. So that 0.4 is like my slope or my rate of change. So 0.4n, or I could use x if I feel like using x. Okay, and I want to do that from n equals 0 till n equals 4. So in summation notation, what that would look like is I'm going to draw out my sum, and I want it to be from n equals 0 till n equals 4. So I'm going to go from 0 till 4. And I want to follow the pattern of 3.6 plus 0.4n. Make that point a little bit bigger. Awesome. So let's try it out, right? If I go to my calculator, I'll type that part in. I'm going to go math, go to my summation, as opposed to n, I'm going to use x, and I want to go from 0 till 4. The pattern is 3.6 plus 0.4x, and I get 22. Done. Okay, so this is going to allow me to kind of add up things that are kind of counting by not ones, but by 0.4s, stuff like that, which is going to be a nice thing for us, like I said, going forward here. So what if I change it to 4 plus 4.4 plus 4.8 plus 5.2 plus 5.6? Well, let's look at this. The next number here would be plus 5.6. So I can literally do the exact same thing, but as opposed to 1 through 4, let's do 1 through, sorry, as opposed to 0 through 4, we'll just do 1 through 5. So if I go back here and I do second entry, and I just change this to going from 1 to 5 as opposed to 0 to 4, yeah, I'm at 24, which is what it would be, right? That's all it is, okay? I've now figured out how I can easily do it from either one of those just by slightly changing that particular problem. All right, so compute the sum from part A by hand and then use calculator to make sure, okay, we already kind of did that there. All right, so now on 91. So suppose 3.6 plus 4 plus 4.4 plus 4.8 plus da 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 until we get to 23.6 is to be expressed in sigma notation where the index number begins at 0. Okay, what is the argument of, why is the argument 0.4 n plus 3.6? So we already kind of mentioned that, right? 0.4 is how much we're increasing each time. That's our rate of change or our slope. And 3.6 is our initial point or our 0. So it's that's why we kind of like starting at 0, not starting at 1. Makes finding that a little bit easier. So then what is the value of n for the last term? Well, to figure that out, we just got to do a little bit of algebra here. Is it 23.6? Yeah, okay. So I can say, well, 23.6 equals 3.6 plus 0.4n. So if I do a little bit of algebra here, I can do, well, 23.6 minus 3.6, and I get 20. So I get 20 equals 0.4n. I then divide by 0.4, and I get 50. So that's my 50th term is what I gotta go to get there, which makes sense because if I'm counting by 0.4s, it takes a while to get to like 20s from the like 3s and 4s, right? So it's gonna be my 50th term. So now let's express the sum in sigma notation, right? So we're gonna go, pull this out. So we wanna do sigma notation. I want to do it from, let's actually write it first before we get there. So it's going to be the same thing, but 0 to 50, right? So I want x from 0 to 50, following the pattern of 3.6 plus 0.4x, summation 693.6. So we can see why we really like a calculator or a program to do this. While you are more than capable of doing that by hand, to do that 51 times and then add up all of those, there's a lot of room for like error, and it's really, really tedious and not very helpful for us just to kind of do that same thing, repetitive task again and again and again and again and again, right? So that's why we really like this notation, and more specifically why we like having a program that can just do all that tedium for us. All right. And then use the same index to express 2.5 plus 2.7 plus 2.9 all the way up to 22.5 in sigma notation, where the index n begins at 0. Okay, so let's try and figure this out. So we have, I'm going to write this down, 2.5 plus 2.7 plus 2.9 plus 3.1 plus dot 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 dot. until we get to 22.5. All right, so let's work through how we can solve this out. So pattern-wise, I'm starting at 2.5. That's like my y-intercept or my b, right? I then want to increase by 0.2 as my rate of change for each change in. So that's going to be my pattern. So all I got to figure out is where I'm going to stop. Well, I'm stopping at 22.5. So when does 22.5 equal this pattern of 2.5 plus 0.2n? If I subtract the 2.5, I get 20 equals 0.2n. If I divide by 0.2, 20 divided by 0.2, get 100 equals n. So I'm going to go to 100. So then my summation for it would look like this. I want the summation from n equals 0 to 100. And the pattern is 2.5 plus 0.2n. So again, they're not asking us to actually solve it out. Let's do it because why not? So math, summation, we want x from 0 to 100. Our pattern is 2.5 plus 0.2x. And bingo, there we go. 1,262.5. So again, your calculator can do that in a matter of seconds. To do that by hand would take you way longer than you'd ever want to spend doing that tedious of math. All right. So hopping back over here. Note-wise, this is what's called subscript notation. Now, we really didn't use this, but we kind of used a variation of it. I just labeled these as 0, 1, 2, 3, and 4, right? They're going to use x sub 0, x sub 1, x sub 2, x sub 3, and so forth. It's doing the exact same thing, but they do that so that you don't get like the number 2 confused with the value of 3. Because if I say, well, 2 is 3, you're like, well, what does that mean, right? But if I say, hey, x sub 2 is 3, that's a little bit more descriptive as to what we're talking about. So that's where we're going to try and transition to from what we just kind of used today as being like, hey, just this is the 0th term, the first term, the second term. It's the x sub 0, x sub 1, x sub 2, and so forth. All right. So just again, going over this notation, we have the big sigma, we have the starting point on the bottom, we have the ending point, and then we have the pattern. This is the argument, and the index is the points where you start and you stop. Typically n or k are used as the variables here. On your calculator, I'm going to use x because it's way easier on the TI-84s, but you can use any value you want. All right. With that, here is our homework for 321. We're doing 93 through 100, and I will talk to you next time.